My name is David Meshnick, and I'll be presenting a literature review on the paper Quantum Algorithms for Feed-Forward Neural Networks by Jonathan Alcock, Changyu Shui, Jordanis Carandes, and Shengyu Zheng. Let's start with the motivations for this research, which lies in the computationally expensive nature of feed-forward neural networks and backpropagation. These are widely used techniques in machine learning, and researchers Alcock et al. Proposed a series of quantum algorithms to reduce the runtime required to train a neural network. I'll first review these techniques, then I'll examine the quantum computing principles used to augment them. This will lead into the algorithms themselves, where along with their experimental results, challenges and future extensions will be discussed. A feed-forward neural network consists of multiple layers of neurons, which takes an input, modifies that by some associated weights, and aggregates them with some bias to produce an argument for a nonlinear activation function. The output is then passed along as the input to the next layer, and this process is repeated. What makes the network feed-forward is that there are no cycles or loops between nodes, and what enables them to be trained is backpropagation. This is a technique that allows for weights and biases of a network to be updated to account for its performance on the input. By repeating these steps of feed-forward, backpropagation, and updating the weights and biases, a neural network can train a model in time complexity O of TME, which is often further increased to account for overfitting corrections. Reframing the feed-forward process as a quantum problem, the researchers introduce estimated inner product calculations with probabilities 1 minus gamma and error tolerance epsilon to take advantage of quantum computing's speed in parallel tasks. In a problem space that is highly sequential, the researchers introduce a hybrid quantum architecture that uses classical computing for the sequential steps of feed-forward neural network training, and quantum computing for the robust inner product estimation, or RIPE. These calculations are enabled by QRAM, which is a specialized quantum random access memory designed for these tasks, and sped up by low-rank initialization and implicit storage. Low-rank initialization sets the initial weights of the network with a lower-ranked set of values, as opposed to the fully ranked weight sets, which reduces the time spent accessing QRAM at the start. Likewise, implicit storage of weights and biases achieves computational savings by storing a subset of the parameters needed to calculate the weights in a matrix such that the weights can be easily determined dynamically instead of explicitly needing to store the full parameter set of the weights. This slide depicts the researchers' three core quantum algorithms for feed-forward, backpropagation, and training. In algorithm 1, the quantum feed-forward method is explained, where the weight matrices are created and RIPE is used to estimate the inner product of the neuron's functionalities. In algorithm 2, the backpropagation method is explained, where the biases are updated in accordance with the network's performance and a cost function C, and RIPE is again used to determine the inner products of the new biases and new weight matrices. These two techniques are brought together in algorithm 3, which formalizes the steps of training a feed-forward neural network using quantum algorithms. The overall runtime of the quantum training algorithm, which is lower than the classical runtime of OTME, is displayed on the bottom right alongside its proof. Alcock et al. Classically simulate their algorithm's results on both the MINST, which is a handwritten character, numerical character image set, and the iris dataset, which is an image set of irises, with different error tolerance values, and demonstrate their resilience to noise. Classical feed-forward neural network training often incurs additional overhead to accomplish this, but the inherent uncertainty of quantum measurements shows acceptable tolerances. In addition to noise tolerances, the theoretical runtime improvements indicate a promising future use case for quantum algorithms in feed-forward neural network training. Furthermore, the researchers explore classical analogies to the quantum algorithms discussed to provide a more traditional estimations. Validating these efforts, however, remains difficult, as the complexity of implementing QRAM in real life is roughly equivalent to creating a fully realized quantum computer with the significant size of storage required for these techniques. Even so, these algorithms showcase a promising future use of quantum computing in machine learning.